FastMCP2's asynchronous task management system employs a non-blocking wait mechanism to coordinate background operations, allowing precise control over completion timing and state transitions. This utility function serves as the primary synchronization primitive for long-running tasks, enabling developers to specify either duration-based timeouts or state-specific conditions. We're about to examine how the wait method gets configured with a 30-second timeout parameter and an optional state filter, demonstrating the framework's approach to conditional task monitoring. The upcoming code snippet will reveal the exact syntax for these two waiting patterns, showing how they integrate with the broader task lifecycle management system.
Hash wait up to 30 seconds for completion. Status equals await task. Wait timeout equals 30, 0. Hash wait for a specific state. Status equals await task. Wait state equals completed. Timeout equals 30, 0.
This code demonstrates the wait function's utility for asynchronous task management in FastMCP2. The pattern provides two distinct waiting strategies, time-based and state-based. The first example shows a simple timeout mechanism, blocking for up to 30 seconds until the task completes or the timeout elapses. The second example adds state specificity, waiting only until the task reaches the completed state or the timeout occurs. This dual approach gives developers fine-grained control over task synchronization. The design choice to separate timeout and state parameters allows for flexible waiting behavior. Time-based waiting is useful when you need to cap maximum wait time regardless of task state, while state-based waiting lets you proceed as soon as a specific condition is met. The timeout parameter serves as a safeguard against indefinite blocking, which is crucial in production systems where responsiveness matters. This pattern is particularly valuable in scenarios where you need to coordinate multiple asynchronous operations or implement fallback logic when tasks take too long. The trade-off here is between precision and simplicity. While these waiting mechanisms provide control, they require developers to explicitly handle timeout scenarios and state transitions. The pattern assumes the caller will check the returned status to determine next steps, which adds some boilerplate, but ensures explicit error handling. This approach aligns with FastMCP's design philosophy of giving developers direct control over asynchronous workflows, rather than hiding complexity behind abstractions. Let's break it down line by line.
Hash wait up to 30 seconds for completion. Status equals await task. Wait timeout equals 30, 0.
Awaits the completion of the task, object with a maximum timeout of 30 seconds. The wait method is called asynchronously, and the result likely a status indicator is assigned to the status variable. If the task doesn't complete within 30 seconds, the call will return early with a timeout status.
Hash wait for a specific state. Status equals await task. Wait state equals completed. Timeout equals 30, 0.
Awaits the completion of an asynchronous task, specifically waiting for it to reach the completed state. The operation will block for a maximum of 30 seconds before timing out. The resulting status of the task is then assigned to the variable status. FastMCP2's wait mechanism provides two complementary approaches to asynchronous task coordination: time-based and state-based waiting. Both patterns leverage the same non-blocking primitive, but serve different synchronization needs. The timeout-only variant caps maximum wait duration regardless of task state, ideal for enforcing responsiveness guarantees. The state-specific version adds precision by proceeding only when the task reaches the desired state, with timeout as a fallback. This separation of concerns, time versus state, lets developers choose between strict timing control and conditional progression. The design explicitly surfaces timeout handling to the caller, trading some boilerplate for predictable error handling. Together, these patterns form FastMCP's core synchronization toolkit, giving direct control over task lifecycle coordination without hiding complexity behind abstractions. The connective insight: both approaches share the same timeout safeguard, making them composable strategies rather than mutually exclusive alternatives.
The waiting task cancels itself, only to discover it was waiting to be canceled all along.